The derivative. The slope of a curve. The key to solving a wide range of problems is the ability to compute the slope of the tangent line to the graph of a function f at a given point a f of a. The slope of the secant line through a f of a and a second point a plus h f of a plus h provides an approximation when h is small. And the exact slope of the tangent line is the limit of secant line slopes as h approaches 0. Here we see what happens as h gets smaller. Notice that the slope of the secant line is getting closer and closer to the slope of the tangent line. The slope of the secant line through a f of a and a plus h f of a plus h is the quotient f of a plus h minus f of a divided by h. This is just an application of the standard formula for the slope of a line through 2 points. This quotient is often called the forward difference quotient for f at the point a f of a. So the slope of the tangent line at a f of a is the limit as h approaches 0 of these quotients. We should emphasize that in order for this limit to exist, the corresponding one-sided limits, as always, must exist and coincide. In other words, we're concerned with both positive and negative values of h. The picture on the right is basically the same as the picture above, but it corresponds to a negative value of h. Let's look at a simple animation here. Notice the tangent line is the dashed line in the picture. The secant line is the blue line. What we'll see here first is the secant line getting closer and closer to the tangent line as h approaches 0 from above, and then the same thing as h approaches 0 from below. A function f is said to be differentiable at a if the limit as h approaches 0 of f of a plus h minus f of a divided by h exists. The value of this limit is called the derivative of f at a and is denoted by f prime of a. In other words, we define f prime of a to be the limit as h approaches 0 of f of a plus h minus f of a divided by h, provided that the limit exists. And when that limit exists, it provides us with the slope of the tangent line to the graph of f at a f of a. Couple of remarks. Since the slope of the tangent line at a f of a is by definition f prime of a, the equation of the tangent line is y minus f of a equals f prime of a times x minus a. This is simply an application of the point slope equation of a line. Y minus the known y-coordinate equals slope times x minus the known x-coordinate. F prime of a is often referred to as the rate of change in f at x equals a. Example. Let's find the slope of the graph of f of x equals the square root of x at 4, 2, and write the equation of the tangent line there. First we form and simplify the expression that gives the slope of the secant line through 4, 2 and 4 plus h square root of 4 plus h. That's f of 4 plus h minus f of 4 divided by h, which is the square root of 4 plus h minus 2 divided by h. Next, we'll multiply the numerator-denominator of the fraction by the square root of 4 plus h plus 2. This makes the numerator 4 plus h minus 4, so we can get rid of the 4's, and then we have h divided by h, which is 1, and so the difference quotient is equal to 1 divided by the square root of 4 plus h plus 2 for all h other than 0. So now we take the limit as h goes to 0 and obtain the slope of the tangent line. F prime of 4 is equal to the limit as h goes to 0 of 1 over the square root of 4 plus h plus 2, which is 1 over the square root of 4 plus 2, or 1/4. Finally, the equation of the tangent line is y minus 2 equals 1/4 times x minus 4, or if you prefer, y equals 1/4 x plus 1. Here's a picture showing what we've found. You see the graph of the square root function, as well as the tangent line at the point 4, 2. The derivative as a function. Given a function f, we define a function named f prime, called the derivative of f, by f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x divided by h. The domain of this function f prime is understood to be the set of all x for which the defining limit exists, that is, at all x at which f is differentiable. Note that wherever f prime of x exists, it is the slope of the graph of f at the point x f of x, as well as the rate of change in f of x. Here's an animation which plots the graph of f prime of x. Notice the tangent line in red and the graph of f prime in blue. We'll see that wherever the slope of the tangent line is positive, the graph of f prime will be above the x-axis. Wherever the slope of the tangent line is negative, the graph of f prime will be below the x-axis. And notice that as the graph of f tends to level off, the graph of f prime is approaching the x-axis. Another example. Sketch the graph of f prime of x given the graph of f on the right. Let's make another copy of the graph of f, and we'll plot the graph of f prime on top. Let's first notice that the graph of f has a negative slope between 0 and 1, and the slope becomes positive on the right of 1. So the graph of the derivative should look something like this. It has negative values between 0 and 1, crosses the x-axis as values become positive to the right of 1. Now the slope of the graph of f remains positive up to x equals 3, where it becomes negative. So the graph of the derivative should look something like this. It stays above the x-axis until x equals 3, to the right of which the values of f prime become negative. To the right of 4, the slope becomes positive again. So we continue the graph of the derivative in such a way that it crosses the x-axis again at 4, and its values become positive to the right of 4. And then we note that the slope of the graph of f simply becomes larger and larger, so the graph of the derivative is continued as we see here. Example. Find f prime of x given that f of x equals x plus 1 over x. First we form and simplify the expression f of x plus h minus f of x divided by h. F of x plus h is obtained by substituting x plus h into the function f for x wherever it appears in the formula. So f of x plus h is x plus h plus 1 over x plus h. And of course f of x is just x plus 1 over x. Now we do some simplification. Notice that the numerator contains x minus x, so the numerator is h plus 1 over x plus h minus 1 over x. So at this point we'll split off h over h into a separate term, and then to simplify the second term, we'll multiply the numerator and denominator by the least common denominator of the fractions in its numerator, x plus h times x. Now, h divided by h is 1, and the numerator of the second term becomes x minus x plus h. X minus x is 0, so our numerator is just minus h. Now we can cancel an h, and we have 1 minus 1 over x plus h times x, which is finally in a form in which we can evaluate the limit as h approaches 0. Therefore, f prime of x is equal to the limit as h goes to 0 of 1 minus 1 over x plus h times x, which we can easily see is 1 minus 1 over x plus 0 times x, which is 1 minus 1 over x squared. We point out that this is a formula that will give us the slope of the graph of f at any given x. Here's the graph of f. Notice that the graph has a slant asymptote. That's actually the graph of y equals x, which has slope 1. Notice that the slope of f is positive when x is less than minus 1 and negative when x is between minus 1 and 0. And notice how this corresponds to the graph of f prime, changing from positive to negative at x equals minus 1. Also, the graph of f has negative slope between 0 and 1 and positive slope to the right of 1, and the graph of the derivative for positive x looks like this. Non-differentiability. A function f is not differentiable at a if the limit defining f prime of a fails to exist. Here's the graph of a function that fails to be differentiable at x equals 1. Let's try to see why that's true. For negative h, a typical secant line looks like the red line shown here. Notice its slope is 0, and it's always 0 no matter how small h is, as long as h is negative. So the left-sided limit as h approaches 0 of the difference quotient will end up being 0. Now let's think about positive h. This is a typical secant line for a positive h. As h gets smaller, that secant line gets steeper and steeper. But notice that it always has negative slope, and that negative slope is getting larger and larger, so the right-sided limit as h approaches 0 of the difference quotient will be minus infinity. Therefore, the limit as h goes to 0 can't exist. Here's the graph of a function that's also not differentiable at 1. Now let's try to see why that's true. A secant line for a negative value of h looks like this. And as h gets smaller, we always have that same secant line, which has a slope of negative 1, and so therefore the left-sided limit as h approaches 0 of our difference quotient at 1 will be negative 1. Now let's consider a positive h. Here's a typical secant line corresponding to a positive h. As h gets smaller and smaller, that secant line becomes closer and closer to being horizontal, and in fact, the right-sided limit of our difference quotient as h approaches 0 is equal to 0. Since the left-sided limit is minus 1 and the right-sided limit is 0, the limit as h approaches 0 does not exist. Here's the graph of a function that's not differentiable at 0. To see why, let's consider a secant line corresponding to a negative value of h. Notice it has a positive slope. As h approaches 0 from the left, those positive slopes are simply getting larger and larger as the secant line becomes vertical, and so we conclude that the left-sided limit is plus infinity. A secant line corresponding to a positive h looks something like this, and as h approaches 0 from the right, again we're seeing positive slopes that become larger and larger, and so the right-sided limit is plus infinity. Notice that the left and right-sided limits agree in a sense. They're both plus infinity. In fact, this example is different from the previous two in the sense that there is in fact a tangent line to the graph there. The tangent line is actually vertical. Here's another graph of a function that's not differentiable at x equals 0. Here's a secant line corresponding to a positive value of h. Notice that the slope is positive. And as h gets smaller and smaller, that positive slope gets larger and larger, and so the right-sided limit of the secant line slopes as h goes to 0 is plus infinity. Here's a secant line corresponding to a negative value of h. Notice that the slope is negative, and as h gets closer and closer to 0, those negative slopes get larger and larger and approach minus infinity. So notice here that both one-sided limits are infinite with opposite sign, and in particular, the limit as h goes to 0 of our difference quotient does not exist. In the first picture, the function has a simple discontinuity. And in fact, any function that has a discontinuity at a number a is also not differentiable at a. Or in other words, if f is differentiable at a, then it must be continuous at a. In our second picture, notice that the graph has something that we could describe as a corner point. It is a point where the graph of the function is not smooth. In other words, there's an abrupt change in the slope at x equals 1 here. In our third picture, the function has a vertical tangent line at x equals 0. In the fourth picture, we have something that we call a cusp. The graph comes to a very sharp point at x equals 0. So these are four primary ways in which a function fails to be differentiable. Example. Let's sketch the graph of f prime of x given the graph of f below. Now we'll work from left to right here. Notice that the graph has a horizontal piece which extends up to x equals minus 2. So the graph of the derivative for x less than minus 2 will simply be that of the constant function 0. Also, since there's a corner point on the graph of f at x equals minus 2, the derivative at minus 2 cannot exist. Between minus 2 and minus 1, the graph has a constant slope of minus 1. So the graph of the derivative between minus 2 and minus 1 is a horizontal line at y equals minus 1. And notice there's another corner point at x equals minus 1 on the graph of f, and so f prime of minus 1 does not exist. Now between minus 1 and 0, the graph of f has slope 1, and so the graph of f prime over that interval looks like this. Now the graph of f has a discontinuity at x equals 0, so f prime of 0 doesn't exist. Between 0 and 1, the graph of f has slope 1, and so the graph of f prime looks like this. Now to the right of 1, the graph of f has a positive slope, and the closer we are to 1, the larger that positive slope is. In fact, the limit from the right as x approaches 1 of the slope will actually be plus infinity. So what that tells us is that the graph of f prime has a vertical asymptote at x equals 1, and f prime approaches positive infinity as x approaches 1 from the right. Notice that the slope of the graph of f decreases for x greater than 1 while remaining positive, which results in the graph of the derivative looking something like this.